Today we are going to solve an exercise under ITC ATC 2020 circuit analysis exercise number 1. The first question is to determine the characteristic of the Thévenin equivalent generator seen from terminal A and B. So we know that the element of Thévenin generator is RTEV and ETEV. So we are going to first of all calculate R Thévenin. We are going to, first thing is to redraw the circuit by represent all the EMF, electromotive force, by the internal resistance only. I'm going to draw the first thing. We have R1. I'm going to replace this by a short circuit. And here we have just two terminal A and B. Here is R1, R2, R3, R4, and we discover that these two elements are connected in parallel. And if you have a resistor connected in parallel with a short circuit, means that even that resistor will be short circuited. So the R Thévenin equivalent will be equal to only RTEV will be equal to R1 parallel R2 plus R4. That is it all. Means that this will give off 1 on R1 plus R2 plus R4. And if we replace all these elements by their respective value, we are going to get RTEV equal to 1 on the value of R1 is equal to 1 on 4 plus 1 on 12 plus here 6. And when you evaluate this will give off the value of 9 ohms. Let me record that value so that you ever next time. This implies that RTEV is equal to 9 ohms. And the second element of the generator of Thévenin equivalence seen from terminal A and B is ETEV. So we are going to disconnect the load and calculate the open circuit voltage seen from terminal A and B. I'm going to quickly redraw the circuit. That will give off the first. Let me change the pen. Here is not a short circuit, is E. Here is E2, E1, R1, R2, R3, R4, and ETEV will be fine here. What I want you to do is to first of all give the direction of each voltage. If you have here the current which is going up, here it means that the current here is I, let's say I, main current I. The one going down here, call I1. Here you are going to say this one will be I3, let's say I2. And the direction of the server voltage, if the current is going up, means that the voltage will be going down. Here the voltage is going down, means that the current is going down, the voltage will be going up. Here we have here going like that, it will be going like that, and here. So we discover that there is no load across across the terminal A and B, means that the current I2 will be equal to 0. Means that by applying the first law of Kirchhoff, we are simply say that I2 is equal to 0. This is because no load. That is it. You can record that value first thing. And if the voltage across R4 is equal to 0, means that ETF will be found between this point and this other one. Let's say this point is called J. That point is called J. The ETF will be found between point J and B. Okay. So we can apply the second law of Kirchhoff in this path, in this circuit. Let's say loop 1, and this other closed circuit, loop 2. We can say that loop 1 will give off, loop 1 will give me E1 minus I R1 minus here, this other point I'm there, minus I R2, because the current going out I2 is equal to 0, means that I will be equal to I1, minus E2 is equal to 0. You can call this equation let's say equation 1. Okay. Now the second equation here in loop 2, we are going started from E2. We are going to write E2 plus I R2 minus ETF, because we said that ETF will be found between point J and B, minus ETF will be equal to 0. You can also call that equation 2. Now we discover that from equation 2 we can get the expression of I1 and go to equation 2, substitute I. So I'm going to take equation 1 will give me E1 minus I bracket open R1 plus R2 minus E2 will be equal to 0. That is correct. From this equation now we can simply say that I alone will be equal to E1 minus E2 all over R1 plus R2. Let's say this equation is equation 3. Now taking equation 3 into equation 2, we will simply get ETF. Equation 3 in 2. Equation 3 in 2 will give me 3 in 2 will give me started from E, it will give me E2 minus I here is equal to this element. This element will be equal to E1 minus E2 all over R1 plus R2 multiplied by R2 minus ETF will be equal to 0. Okay, we are going to arrange the thing in order to get there. Means that E Tef alone will be equal to, sending E Tef in the other hand, we cross the equality by changing the sign. By changing the sign, it will give me let's say E2 minus E1 minus E2 on R1 plus R2. This is the expression of ETF. By replacing in element by their respective value, by replacing each element by their respective value, we have all the value there. We are going to get the ETF. ETF will be equal to E1. Let me check the notes here. E1 alone is equal to 8 volt minus 20 minus 8 all over 4 plus 12. When you apply this equation, it's going to give 8.75 volt. This implies that ETF RTF will be equal to 8.75. ETF equal to 8.75 volt. That is the value of ETF, and we said that we find in the previous section we got RTF equal to 9 ohms, means that we have solved all this equation, the first equation. So let me record that value here. We said that RTF equal to 9 ohms and ETF equal to 8.75 volt. That is it. Let me go down and continue the second exercise. Now in point B, they ask us to deduce the corresponding Norton equivalent model. The Norton equivalent model. So the first thing is to give the equivalent Thévenin model. We have internal resistance, we have EMF, ETF, and here is RTF equal to 9 ohms and RTF and ETF equal to 8.75 volt, and you have the terminal A and B. Now in the next point, we are going to find the equivalent Norton circuit. The equivalent Norton circuit is equal to, let's say we have that RTF, the internal voltage, RTF, ETF. This will be equal to the equivalent Norton circuit will be equal to current source in parallel with an internal resistor, which is R Norton, and here is I Norton, and here I Norton is equal to ETF all over R TEF, and R Norton alone is equal to R TEF. So we can simply say that, compare it to what we saw, that R Norton is equal to 9 ohms and I Norton is equal to R Thévenin is equal to 9 ohms divided by, E Thévenin E Thévenin is equal to 8.75 volt divided by R Thévenin, which is here 9 ohms. And when you apply this, we are going to get 'Give me the time to calculate so that 975 milliamps. When you apply this, means that 0.9797 amps. This implies that I Norton is only equal to 972.22 milliamps. Okay, that is it all. Now the second point has been calculated. We are going to write like that. R Norton is equal to 9 ohms and I Norton is equal to 0.97 amps. Let us move now to the next point. Calculate the value of current I in the load resistance R and the voltage drop across it if the resistor of 20 ohm is connected across. Now, if the resistance of 20 ohms is connected across, let's say we have here the internal resistance of RTEF, the ETEF here, we have the two terminal A and B, and we said that we connect the resistor of 20 ohm. That is what have been gave. B here RTEF here is 9 ohms, ETEF here is 8.75, and the resistor. Now let us find this current, the current flowing in the circuit if that resistor is connected, as well as the voltage across that resistor. Let's say that voltage is equal to U. By applying the second law of Kirchhoff inside this closed circuit, we can simply write like this. The current is going up, means that the voltage will be down. Okay, we have all the elements. We can simply write the second law of Kirchhoff in this closed circuit. In this closed circuit, we give off 8.75 minus that current I times 9 multiplied by 9 minus 20 ohm. The same current I, because the current flowing through 9 ohm resistor is the same as the current flowing through the 20 ohms, minus I times 20 is equal to 0. By putting I outside, we are going to write 8.75 minus I bracket open 9 plus 20 equal to 0, means that I alone will be equal to 8.75 volt divided by 29 ohms. And if you apply this, we are going to get let me open, use my calculator and get, we are going to get 0.301 0.3 amps. That is the current that has been asked. if the load of 20 ohms is connected across that circuit, we are going to get the current of 0.3 amps. Now, what is the voltage across that 20 ohm resistor? By applying the Ohm's law, we said that the voltage U will be equal to I times R. By applying that equation, Ohm's law, you get that current I is equal to 0.31 amps times 20 ohms will be equal to 6.034, approximately 6 volt. Means that voltage is equal to 6 volt. Let us go up and replace. I got 0.3 for the current and 6 volt for the voltage. Means that here we are going to say that voltage is, that current is equal to 0.301 amps, and that voltage is equal to 6.01 volt. Now, the last point now, determine the value of R to obtain the maximum transfer power, Pmax. In order to get the maximum transfer power, the resistance of the load should be equal to the resistance of the source. In that, to get the maximum transfer power, in this circuit, so we have in this circuit the resistance of this load here should be equal to the resistance of the antenna, should be equal to the resistance of the internal. The resistance of the load should be equal to the internal resistance of the source. Let me redraw the circuit so that you can simply understand what I'm saying. You have the internal resistance of the source here and the voltage, which is E def, and you have, if you connect the load, the variable load here, R, E def, R def. In order to get the maximum transfer power here, the resistance of P, to get Pmax, the resistance of the load should be equal to that R def. That is the condition to get the maximum transfer power. Means that in this case R will be equal to 9 ohms. If R is equal to 9 ohms, what will be now the value of that power? By applying the formula of the power, you can say that P is equal to, we have several formula, I times U, if you have current and voltage, equal to I square R, if you have all these elements, also equal to voltage across square divided by the resistance of the source. Why? In this case we have the resistor, but we don't have that maximum current. To get that maximum current, we are going to find the maximum current. We are going to find the maximum current. The maximum current here should be equal to I, equal to the supply voltage here is equal to E def divided by the resistance of the source, E R def, plus R, which is equal to 8.9, 8.75 volt divided by 9 plus 9 ohms, and this will give off a value of 0.486 amps. That will be the maximum power current that we are going to get. Now, by applying now this equation, because we have resistor, we have current, we can apply this formula in order to get the Pmax. As I have already calculated that element, let me wipe that other part. No, leave like that. Pmax will be equal to I square 0.486 square multiplied by the resistor, and the resistor here is 9 ohms. When you apply this, you are going to get 2.126 watt. 2.126 watt. That is the value of that power. Okay, let us go up and record that value. So the resistance of the source here, R should be equal to RTEF equal to 9 ohms, and Pmax is equal to 2.126 watt. That is that power that will be asked. So we have finished with that exercise. If you have the equation, don't forget to ask in the description section below. I will be happy to answer that question for you. And if you are new in this channel, don't forget to subscribe to the channel